So the idea here is to share with you some of less known Group 4 semiconductor systems, and the argument here is that these systems can bring to the table some new properties without losing the silicon compatibility and what comes with it in terms of manufacturability, scalability, and control. So the talk is a little bit broad, but the idea is very well defined. So here, working with the planar heterostructures means that something that we can produce in wafer scale, and we do actually produce that in wafer scale, and we leverage two main properties. So one of these properties is the tunability of the band gap in these group force systems. But let me just give you an idea about the broader context of this work. So the group 4 semiconductors that we are interested in are basically germanium, silicon, and tin. And if you look at just what is the story here on the right side, you see that I'm showing you the band gap and band structure in these three elements. And I don't need to remind you that silicon is an indirect band gap, germanium is an indirect band gap, and tin in a diamond phase, it's a semi-metal with inverted band gap. So if we take tin and you mix it with these two elements, it's possible to tune the band gap. And I was showing you here one example. So this is the band gap, indirect band gap of germanium. If you put a little bit of tin, about 10%, it's not a little bit, it's a lot if you consider other constraints, you will obtain a direct band gap material. And this is very interesting because you can detect efficiently or emit efficiently light. And here in this figure, it gives you the entire landscape. So on the top, this is tin composition, and here you will see the germanium and how the L value drops as a function of tin content, and you see that gamma value drops much quicker, and there is a crossover exactly around close to 10%, between 6 to 10%, depending on strain. And the interesting thing here is that you can cover the entire infrared band by just tuning the composition and also strain that I'm not showing here. So adding silicon, basically you can mimic all the 3-5 structure. We can tune independently the band structure and the lattice parameter. So this is one side of it, and by itself it actually stands, and you can do a lot of interesting things in terms of photonics and optoelectronics, all based on silicon. But the other element that is unique to Group 4 is that this element have a few stable isotopes, and this will give another knob to play with, which is the nuclear properties and also the average mass in the lattice. And you can see here that I forgot to put a star here. So basically, for each element, you will have a few isotopes that are nuclear spin full. And that's an additional knob that you can play with. So you can either remove this nuclear spin background, or you can engineer it and create even quantum dots localized that are made of this local magnet. So in my lab, I'm trying to play with these two properties and combining the two of them. So in one hand, you can do what is conventional, playing with the band structure and trying to engineer light-matter interaction. And you can engineer conventional devices from lasers, light-emitting diodes, single photon detectors, and so forth. On the other hand, you can play with isotopes, and here you have something that is unique. You can change nuclear spin distribution. You can play with mass disorder, and you can create a lot of subtle processes. And if you can control them, you can obtain a unique platform that is hardly achievable in other systems. So, and it's not easy. So, because that will bring another challenges. So this is how I see this niche of research. This Group 4 semiconductors gives you exactly what you can find in any textbook in terms of engineering heterostructures. So be it confinement, defect, and strain. And on the other hand, you can use this isotope to control phonon engineering. And I remember Samik, his entire PhD about playing with phonons in this isotopically controlled silicon. And you can control, as I mentioned, nuclear spin distribution, band gap as well, and lattice disorder. So you can create locally disorder. Think of it as harmonic oscillators. So you can just remove some of the heavy or light isotopes without changing the electronic structure or without affecting or changing the chemistry or the chemical composition of your materials. So this is, if you combine the two, you will have a very rich platform. So you can do a lot of interesting physics with these systems without losing the technological relevance. So I'll remind you here that everything is built on silicon, which means that any device that shows any interesting properties can be really manufactured and can be scaled. And that comes with a very strong technological and industrial interest. The main challenge, or there are two main challenges. The first one is controlling these processes and growing materials that can give you exactly what you are looking for. And the second one, especially when it comes to these subtle processes, one has to have the right metrology in order to probe and confirm first the composition, distribution of different isotopes, and also whatever processes that are based on this very subtle isotopic effect. So this is the big picture. This is where I live since I started my lab. And now I will step back and I'll give you one example. I could have, for instance, picked photonics or quantum optics as the main door to show you the interest behind these systems. But since this is more in the spin-based devices, so I will focus on that very aspect. But my focus will be mainly on how we make materials, how we characterize materials. If you have any questions regarding transport, some of the structures that we have already have transport measurement and quantum dot fabrications. You can ask me questions. Others are still very challenging because they are not a very mature platform. So we need still to develop all the processes in terms of devices. So let me just give you the context behind the interest in controlling the spin. So this is all the different hardware used in quantum or potentially for quantum processes. Superconducting circuits, you have trapped ions, you have topologically protected systems, color centers, the diamond, silicon, and so forth. And our interest is more in the quantum dot, which is a structure that is inspired directly from transistor architecture. So what is common to these heterostructures or to these platforms, regardless of the physics that is used in order to control these two-level systems, is that it's still very challenging to have either a very large number of devices that behave in a very controlled manner, or sometimes just locally there is a strong variability between devices. And there are other issues. But if I look at this from a very specific materials perspective, we see that a lot of challenges are coming from deep atomic level material properties. So even superconducting circuits, you have this interfaces between metals and dielectrics, and those interfaces are controlling the entire behavior of the material. So basically, all the field was actually based on what the physicists did. They work with a platform that they are familiar with, and they hammer everything regarding device processing without going back to drawing board and engineering material from scratch. That process takes a lot of time, and sometimes is not that glamorous. So there is, if I put this in three different aspects, so there are defects, there are impurities, and there are heterogeneities in these materials that need to be understood. And as you know, a device is based on an interface, and without controlling these interfaces, it will be very difficult to have a tight control over the performance. So if I look at how we can structure the frontiers of materials research, there is a lot of too many gaps in understanding what happened at the atomic level or microscopic level. We need new materials, because if you look at, I will give you a few examples in a moment. If you scratch the surface, you will find that all the materials used are not that many. So as I mentioned, people, they take a platform and they focus on more in a vertical manner and exploring the properties of that platform, especially from a device perspective. So yeah, and once you solve these challenges at the atomic level, one should actually address the scalability, how we can make sure that we have uniform devices across a large system or large area, and also how the entire integrated system will be behaving. So as I said, one can make the case regardless of the material system, but we'll be focusing on heterostructures used in quantum dots. So something that you know, which is the single spin quantum dots. There are different flavors. So this is a slide I got from Giordano some time ago. Just this part. There's a large number of people working on MOS structure, which is basically confining an electron at the interface between a dielectric and silicon. A large number of people working on silicon germanium, and here you are confining an electron in strained silicon. And more recently, there is a lot of interest in germanium confined, quantum oil based in germanium grown on silicon germanium layers. And here you will be confining a heavy hole and using the heavy hole spin. If you look at the evolution, so the things are a little bit slow, but there is a lot of hope that things will actually explode given the interest in this hole-based spin qubit. As I mentioned, my group is more interested in tin-based alloys, and I will show you in a moment what are the heterostructures that can be engineered and what is the rationale behind using this germanium tin to engineer new heterostructure. So look at just in the right side here. So this is exactly the top, the two heterostructures I mentioned. So you can either work with an electron spin. This is silicon germanium, and I'm sure that people, Sadhu has been working on this, I think. The challenge on this heterostructure is that you're working with electrons in the conduction band of silicon. Conduction band of silicon is messy. And it comes with a lot of problems and value split in one of them. And you're working on a system that is highly strained. There are dislocations, so there may be variabilities coming from modulation of strain at the surface, alloy disorder at the interface as well. So, and the heavy hole. Now I want you to look at right here in the left. So this is germanium is presented as a solution to all these problems that silicon might have. Instead of having all this and their valley scattering, you will be working with a single valley system. It's like a textbook. It's a very clean environment. But you will have, once you grow germanium or silicon germanium, you create a compressive strain. This is bulk calculations, so it's not confined in the quantum well. But the point here is that if you have a compressive strain, you left the degeneracy, so the valence band, the ground state of the valence band will be heavy hole. So germanium will come with certain advantages. As I mentioned, the valley is very clean, but also you have a large atoms. You have a strong spin orbit coupling, which means that you can instead of having to put a magnet close to the quantum dot, here you can use just electrical fields to control the quantum dot. So we use EDSR, or electron dipole spin resonance schemes. And you have the same advantages as in silicon, so you can remove hyperfine interaction by removing the isotopes. The other advantage is that you can have a strong G factor anisotropy. So at the bottom, I'm showing you another system, and this is something that can be connected directly to this band structure. So if you create a tensile strain in germanium, you will also leave the degeneracy, but your ground state will be a light hole. And light hole will come again with a different, slightly different physics. And it can actually allow you to have a strong coupling to light. So coupling to light is something that I will be addressing with you today. So it can be done either with a light hole ground state or a heavy hole ground state. So I will show you how we make these materials and what is the rationale behind controlling the light hole confined state in germanium. And there is another straightforward way to make the heterostructure optically active. So you take the same band structure as in the germanium or silicon germanium, but you will produce it with using germanium-10 between germanium. So here, your quantum well will be germanium-10, will be a heavy hole character in your ground state with the valence band. But instead of having just germanium, which is direct band gap, compressively strained, you will have a direct band gap germanium-10. So you will have a heterostructure that can interact effectively with light, and it can also emit light. And the interest behind this is, fast forward in the future, if all of this business is successful, people will have stationary processors that are based on spin qubit or any qubit. But you, either for distributed quantum computing or for quantum networks, you need to interface this stationary qubit with a flying qubit. So you need to transmit information using light. And here you have to think about different schemes and different material systems that will allow you to couple effectively optical photons with spin qubit. So just if I look at just the germanium system, there are different ways for achieving this. So if you look at, I will start with the figures at the bottom. So this is, you apply a magnetic field, an in-plane magnetic field. And if you have a heterostructure that is having a light hole in the ground state, and if you make sure that the G factor in the conduction band is very small, you can actually transfer the superposition from the photon, a flying qubit, directly to electron spin in the system. But you have to have a light hole ground state. So this heterostructure requires the G factor engineering. So basically, the Zeeman splitting in the conduction band, this splitting should be smaller than the width of the light that we are using. The second, or the scheme on the right, here you can work with a heavy hole ground state. You don't need to engineer the G factor, and the superposition is transmitted directly to the heavy hole spin. The other schemes, so the one on the left, top left and top right, the two of them require an out-of-plane magnetic field. And one in the left here, you have to use two different photons, two different wavelengths for each, one for each polarization. And the second one, the superposition is not transferred. You obtain at the end an entangled electron-hole pair. So the two configurations at the top are not ideal. So there is now interest in actually achieving this configuration. So I will just show you here how, if you have a germanium hole, a quantum dot, and if you have a G factor that is sufficiently small and for the heavy hole, and you apply an in-plane magnetic field, you can actually achieve this transfer of superposition to whole spin. And this is achievable because the measured G factor of heavy holes is around 0.3, which is enough. And there are calculations. This is from Akira Oiwa from Osaka. The figure I actually got from him. So it's possible actually to engineer a structure. It may require some doping, but no one has demonstrated that yet. In this paper, this figure has nothing to do with the paper. So this is a paper from the same team in Japan, and this includes also Tarosha. Here they achieved the momentum transfer from a flying qubit directly to gallium arsenide, aluminum gallium arsenide heterostructure. It was a heavy hole, similar to this structure. The problem with this, and this is the case, if you remember the first picture I showed you, the first spin qubit was actually in 3.5. And the problem with 3.5 is that all elements, they have nuclear spin full, and which means that they are all nuclear spin full, which means that the hyperfine interaction will limit the coherence. So this is the broad context of what we want to do. We want to have group 4 heterostructures. We need to remove nuclear spin, and we need to design heterostructures that will allow us to strongly couple optical photons with the spin. So I'll start with the first element, which is how we can surpass what can be done with 3.5. So can we create heterostructures that are entirely nuclear spin free? And here a little bit of once people start showing interest in whole spin qubit, one of the arguments is that, well, it's the hole is p-type symmetry, so the coupling to the nucleus is very weak. So people were expecting that the hyperfine interaction to be limited. But limited does not mean that this coupling does not exist to the nuclear spin path. In our recent, this is a paper from QTIC last year. They showed that the presence, so this is a heterostructure like this. So in germanium, we will have germanium-73, and in silicon germanium, we will have germanium-73 and silicon-29. And this is just the natural abundance. So you have 4 to 7%, but it's just this amount of nuclear spin has been a limiting factor in the behavior of the performance of whole germanium on silicon germanium whole spin qubit. And you have in germanium 73, you have a 9.5 nuclear spin, and this spin not only coupled to the whole spin, but also the orientation of spin will impose constraint and configuration of magnetic field that you want to use in plane versus out of plane. So you cannot leverage the G factor anisotropy. That is one of the arguments why whole spin is really interesting. So I'll start to show by showing you what we are doing in terms of achieving this this platform without any nuclear spin. And quickly, I will be showing some results based on atom probe tomography. So I'll give you a quick idea about the root facility that we have in Montreal. So we have CVD reactors that are 4-inch wafers. And in silicon precursors, so we have 4 nines in silicon 28. This is silane. And we have also silicon 29 silane and silicon 30 silane, but this is something that we rarely use. In germanium, we have monogermane, which is the supplier say that is 99.98. This is what was guaranteed. But what is really interesting is to see that germanium 73, which is a nuclear spin full element, the concentration is extremely weak. The same thing here in silicon 29 is it's close to the sensitivity of the method used to measure. And we have also an MBE system equipped with silicon 28 and germanium 72. 10120, we never used it so far. We are still just making sure that it's pure enough that we can use it in our research. So the data I will be showing you today is all based on CVD growth, be it silicon germanium or germanium tin. And for the measurement, as you can see here, we can probe the distribution of different isotopes. This is just an example. The colors here, this is silicon 28, silicon 29, silicon 30, and the 5 isotopes of germanium are given by these colors. So this is a quantum well that is made of germanium 70, and the barrier as a mixture of silicon 28 and other isotopes and germanium 70 and other isotopes. So the image that you see here, this is an image obtained by atom probe tomography. And because I will be based all the analysis on atom probe tomography, I will show you quickly. In our lab, we have an Inviso 6000 instrument. So basically how it works, you take your specimen for people who are not familiar with the method. So you sharpen your specimen in a needle-like shape. And after that, you put it in your atom probe tomograph. And you apply a voltage in a way that the field at the surface will be sufficiently strong to nearly ionize species at the surface. So, and you come with a pulse laser. And this pulse laser will give the thermal energy necessarily to the atoms at the surface to ionize. And once ionized, they will be accelerated by a voltage toward a position-sensitive detector. So here, the time that the ion will take from the surface of the tip to hit the detector is the time of flight. So basically, this is directly related to the mass to charge ratio of your ion. And the detector will record X and Y position. And as you go slowly, you will be removing one layer at a time. So that will give you the Z. So you would have X and Y and Z and mass to charge ratio. So this method is the only one that can give you, with almost near atomic resolution, not only the position of atoms, but also the difference between isotopes. You cannot do that with electron microscopy. So you can see defect, you can see position of atoms, but you cannot distinguish between isotopes. So this is why we spend a lot of time investing in this method. So here an example. So this is a quantum dot in silicon germanium. This is silicon-28. And this is basically a 3D map that you obtain from atom probe tomography. So the red is germanium. So you see this is a silicon germanium barrier. This is a silicon germanium barrier. And here you have a silicon-28 quantum well. But you see within your quantum well that you have some interdiffusion of germanium. This is not surprising, so because this is the bottom barrier. The bottom barrier is annealed longer than the top barrier. So this interdiffusion, as I said, is expected. But you can see here, this purple spheres, this is silicon-29. You can see them. So there is some, gives you some idea about the background doping from other isotopes in the reactor if you don't actually consider carefully engineering or tuning the growth process. I will come to this in a moment. So you can look at in 3D, you can go inside actually and see where the isotope was located and what is the roughness of your interface, what is the alloy disorder at the interface. On all of that information can be actually given to theoreticians, so you can actually model this realistically, not just assume that you have a box-like confining potential, because it's not like that. It's the interface in quantum wells is more a three-dimensional landscape rather than one-dimensional landscape. So this is all about atom probe tomography. Is there any question regarding this? Or I can keep going?
Yeah, you can keep going.
Okay, so let me now take you to the challenge in germanium heterostructures. So all the CVD growth was done in hydrogen, with hydrogen as a carrier gas. I showed you that we are using monoisotopic precursors, silicon-28, silicon-70, and we are mixing also with natural germanium. One element that we need to consider is that these precursors are very expensive, which means the growth process should consider how much you consume. And since all suppliers, or the few suppliers that exist worldwide, they are only producing monogermane and monosilane, those precursors are not the efficient precursors for the growth, which means they require either high temperature and you have to waste a lot of gas in order to grow material. So with that in mind, so we have to engineer the right recipe in order to achieve isotopic purity, but also not to consume too much of that gas. So this is an example of a reference structure. So this is a natural quantum well with natural barriers. And you can see here, the orange spheres are nuclear spin. So your quantum well, and this volume here is equivalent to a quantum dot volume. To give you an idea how many nuclear spins you have. So I have too many. And the same thing in the barrier. At the barrier, you will add also silicon-29. So how we grow this? So ignore now all about isotopes. We start with a silicon wafer. And once we have, we load the silicon wafer in the reactor, we grow a very thick germanium layer. We call that germanium virtual substrate. So this is roughly from 1 micron to 3 microns, but I think the best materials are anything above 2 micron. It gives us a good quality material. And once we grow this germanium layer, we start progressively growing silicon germanium graded buffer. So basically what we are trying to do is we're trying to engineer the lattice parameter until we reach the composition that we want. An example here, 18% silicon and 82% germanium. We can keep growing the same structure, and that will give us a fixed surface lattice parameter in which we can build the entire structure. So just to give you an idea, so this is typically a 2 micron. This is typically another 2 micron. This is about 4 micron. And after that, you add almost 1 micron of relaxed layer. And after that, you grow your germanium quantum well, typically between 10 and 20 nanometer. And on the top of it, you grow a silicon germanium barrier, which is typically between around 50 nanometer. And you finish the structure by a silicon cap, which is 1 to 2 nanometers. Silicon cap here is just to protect the surface, and it's a lot easier to clean silicon surface than cleaning silicon germanium surface. Now, if you want to do this with isotopes, meaning that you can take silicon-28 and germanium-70, and you can grow the entire stack, this is a few micron with this isotope, and that will be extremely wasteful and extremely costly because all your device will actually be built based on this interface. So we are creating a structure that is microns and microns thick to only use the top 60 nanometer. So that's a major problem. But I'll show you here different design that we tried to use in order to achieve isotopic purity without wasting the material. So we go to the reactor. What we do, we say, okay, let's start with natural precursors. So natural germane, natural silane. And we grow until we get to this silicon germanium relaxed layer. And once we get closer to the quantum well, if you will, we switch to germanium isotopically purified, here germanium-70. So we grow a few hundred nanometer of isotopes. So instead of growing microns, we grow only a few hundred nanometer. And we tried with different thicknesses. This is 290. This is 1 micron. This is another 1 micron. And we added another 900 nanometer with silicon-28. So basically we found, if we look at atom probe tomography, so in sample A, so this is a natural quantum well, so this one. Here you can see the mass spectra. So this is the red line, and you can see the 5 isotopes. This is a log scale, which means this is the intensity of these peaks is exactly the natural abundance of germanium isotopes. And you can see that germanium-73 is clearly detectable. Now, if you move to the second type of growth here, when we switch at a certain point with germanium-70, this is the blue line, we still see that in the quantum well, so this is, we analyze only the top a few tens of nanometer, so the area here, we still see a significant amount of germanium-73. And which means that 200 nanometer is not enough to actually suppress any background contamination from natural precursors. And if I look at the structure that provided almost no detectable amount of germanium-73, it's the sample D, which means that we grow 2 micron with isotopically purified materials. And again, for this 2 micron, we are going only to use the top 60 nanometers. So this is a lot of waste. So what we look at here, by looking at the 3D distribution of different elements in the isotopes, we can measure the nuclear spin distance. So how far nuclear spins are apart from each other. And you can see here that natural samples, it's in the best case scenarios in the quantum well, it's about 1 nanometer. So for each 1 nanometer, you see that there is a nuclear spin. And the sample that is more optimized, so this is about 4 nanometer or 3 nanometer, the distance between isotopes. So it's still, it's not detectable here. The problem when analyzing with atom probe with this germanium isotope, there is a lot of overlap between different masses or different peaks, which means that the sensitivity is greatly degraded. So we have to establish a method in order to extract exactly the amount of different isotopes. So even by wasting the growth of 2 micron, we didn't get rid of nuclear spin. So switching, the conclusion here is that switching the progressively the precursor from natural to isotopically purified, it's not a very good idea. So that's always our conclusion. It's very wasteful, and you have natural-contamination. So this is a reservoir effect, which means that within your reactor, we still have natural germanium isotopes and natural silicon isotopes. So what we decided to do is actually to go to industry and we ask industrial several companies to grow for us silicon germanium buffers, and they send us those buffers, and we in our reactor we don't use any natural precursors anymore. So this is how it looks like. So this is, we decided to work in 200 millimeter wafers. So the whole stack. So this is just the lattice parameter that we need to have. It's done ex situ, and the top structure, which is purely purified, isotopically purified, is done in our reactor. And typically with 200 nanometer, we get the entire infrastructure. This is the good news. It worked. But one of the challenges, as I mentioned earlier, starting with a silicon substrate in a CVD reactor, it's a lot easy wafer to work with, because cleaning silicon, you have a certain oxide that we know exactly how it behaves, and it's well established, and you just anneal at high temperature, you put hydrogen, and you do all of this with chemical cleaning before. But once you start with a silicon germanium wafer, so we have two different oxides. We have silicon oxide, germanium oxide, and we spent, I'd say, more than a year and a half just to optimize the cleaning of silicon germanium wafer. It's a very tedious process, and whatever recipe you have, it's not the same if you change the stoichiometry. So if you are working with 20% silicon, the cleaning is different from 30%. So the fraction of different oxides will play in a circle. So once we have this, we went through all, I will show you a different characterization, isotopic distribution, and also we did some transport measurement to look at mobility. I don't have any, I might have the data, but not the result, but not the measurement per se in this presentation. So here's it. So the TM image here, it shows the interface between the industrial, that's this black band here, so between the industrial buffers and what we grow. And you see that we have a little bit contrast here. So it was a little bit of germanium segregation at that interface. But you can see clearly that there are no extended defect. And if you zoom in near the surface, you see that the isotopically purified quantum well, it has very well defined interfaces. And in the reciprocal space map, X-ray diffraction, we see that the barrier that we grow, so what we grow here, what we call here overgrowth, is exactly the same composition as the silicon germanium buffer. So that recipe works fine. Now this is a very complex figure showing the isotope distribution. So what you see here in purple is exactly here. And this is the interface that you see here. And here is silicon germanium buffer, relaxed layer grown on the industrial buffers, but using isotopically purified. Everything from this point to here is grown in isotopically purified, in the reactor with isotopically purified precursors. And what you see here, it's all the isotopes. This is in ppm without germanium 70, and here all silicon isotopes without silicon-28, oxygen, and carbon. So you see that the interface, so this is where we start cleaning before the growth. We still have some traces of oxygen. And again, this is about 100 ppm. And if we move to the right, and this is what was grown with isotopically purified materials, you see that germanium, we have only germanium 70 isotope and silicon-28 isotopes. By the way, this is atom probe tomography profiles. Now we get closer to the quantum well, so we can see the distribution of silicon-28. So there is no silicon-28 in the quantum well. And we have almost 100% of germanium 70 in the quantum well. There is issues with the interface in this measurement, but it's, as I said, it didn't affect much the behavior at the device level. The good news is that there are no other impurities, so carbon oxygen is below the detection limit. So by looking carefully on the entire maps for the different materials, so basically we have 0 ppm germanium 73 and a little bit of germanium silicon-29. This is the entire heterostructure. But again, this is really close to the sensitivity of atom probe tomography. I will not give too much, I will not take this too seriously. Mobility measurement, I think this is at below around 1.7 Kelvin. All devices show mobilities that is above 230,000 and percolation density below 17 to 10. So this is on par with the best heterostructures reported using natural silicon and natural germanium. And I think all of this mobility measurement are not limited with the material quality, but rather limited by the device processing. So we have this interface with the oxide that still need to be optimized. Yeah, if we look at now nuclear spin distribution, what we found is that pausing the growth. So we start growing using just germanium-70 and silicon-28. When we stop at this interface a little bit, and after that we continue the growth. So this is silicon-germanium buffer, silicon-germanium barrier. We see the difference in terms of the chemical composition, but also a nuclear spin. So if you waited a little bit, this is if you wait 90 seconds at the bottom interface and the top interface, we saw that there is some germanium-73. So the reactor still has some memory effect or reservoir effect that we can still see some nuclear spins. But if we shorten that growth pause to 30 seconds, we achieve a much better structure. If you ask me why we are using this pause, is that I mentioned earlier that we have a slight jump. If you go back, we have a slight jump in silicon composition at the top interface, and we were concerned that this interface compositional fluctuation may affect devices. So we spent time in controlling that interface. And here we found a 30 second with a boost of silicon-28. So we stop 30 seconds and we increase the amount or the flux of silicon-28 silane. We achieve a clean growth. What you see here is one germanium-73. This is just a statistical anomaly. And in general, this structure remains nuclear spin free. And here is this is a silicon atom probe tomography heat map. So this is what I mentioned. So this is exactly the same recipe. And if you look at the 30-second growth pause with a boost of silicon silane, you see that the interface here, the fluctuation in silicon composition is limited, and you can see in other growths, we have a large fluctuations. Long pause, no pause. It gives this jump in composition. So we decided to work with this heterostructure. All okay?
Yeah, Oussama.
Good. Okay. So here I would like to just to conclude this part. So basically, and this is the entire community working on silicon germanium, on silicon germanium, they have, when you switch to isotopes, you have to engineer your reactor not to consume too much of these precursors. And second is you have to engineer even the substrates in order to avoid this wasting this element. A small bottle, if you put it in an industrial reactor, you might just open it and you fly. Everything will go away, and you cannot grow enough samples. So here, what we showed is that by working with ex situ, the silicon germanium surfaces, we can solve part of that problem. And something I didn't mention, we also modified the hardware of the CVD reactor in a way that we can only supply a small amount of precursor without hampering the growth rate. And we are still waiting for other groups to show germanium 70 or nuclear spin-free germanium quantum well, so we can compare with their result. I know that there are at least two groups working with germanium 73 depleted precursor, but they might have issues with oxygen carbon contamination and the precursor. So we will keep our eye on this. We have some quantum dot processed using this, but we still don't have any measurement that show any conclusive result regarding the advantage of removing nuclear spin. I think that the behavior may be actually a combination of both noise and hyperfine interaction. So now I will move to what I mentioned earlier, which is how we can achieve an optically active quantum dot. And here, what we want, basically, we want to have a quantum well that is direct bandgap, and which will allow us to have a strong gamma to gamma optical transitions. I want to have indirect bandgap barriers. So we don't want the barriers to interact strongly with light, so we need the light to go directly to quantum well. So typically we need to achieve a heterostructure that will give us a direct quantum well with germanium as a barrier. So if you take germanium tin and you grow it on a relaxed germanium, you will be always in this white area. This white area is when your bandgap is indirect. But if you start straining germanium, so here your germanium will become tensile strain, you will push the structure toward this area, where the colored area, where the quantum well become direct and the barrier are indirect. If you go higher in terms, so we look at this is the quantum well composition. So if we say, okay, we'll be working with 0.75% compressive strain in the quantum well, so that will be a heavy hole character. So to get a direct bandgap quantum well with the indirect bandgap barrier, I should be close to 15% to 14% tin in my germanium tin quantum well. So basically, what if you are in this band? So we look at now the band alignment. So if I'm in the left of this line, I will have the heavy hole buried in the continuum of light hole. And if I move slightly to this narrow band, I will still have issues with the confined state of the heavy hole. It's still close, buried in the light hole continuum, but it's not that bad. There is a small offset between the two. But I need, if I move to the green zone, here my confined heavy hole state stays above the continuum of light hole, and this is exactly where I want to be. So I want to be in the right of this dashed line. I want to be in the top, above this line, and below this line. So basically, I want to be somewhere here in this zone, which is obviously, it's the most difficult part to grow with materials. So basically, you need to have stronger tensile strain in germanium, and you have to have strong tin incorporations. Anything should be above 15% to be in the safe side. So before I show you some of the experimental results, what we did, we look at just in the theory. So if I pick, as I mentioned, somewhere a quantum well in this area. So here I have 15% and tensile strain germanium, which was grown in 8% germanium tin. And we look at all characteristics of the heavy hole, EDSR controlled hole spin. We found that the material behaved exactly like a heavy hole in germanium. So all the features, the G factor anisotropy, also the dipole and the Rabi frequency, all of them behave exactly how the same way as germanium or silicon germanium, except that this quantum dot, it has a direct bandgap, which means that it can interact effectively with optical photons. So, but now the challenge is how to grow this. And I will give you just a quick idea how we grow germanium tin in general, because the key is to achieve sufficient relaxation in this buffer layer. And after that, controlling the growth with germanium, that will be tensile strain, and the growth should be, the layer should be thin enough so you don't create dislocations, so below the critical thickness. And after that, you switch to germanium tin growth at 15%, at much higher composition, and you cap with germanium. So this is really the difficult part in growing these materials. So what we do in general, so everything is grown in a CVD reactor. We start with a silicon wafer. We have, this is a shower head reactor. And for germanium, we use germane. And for tin, we use trichloride tin. So it's the same as I mentioned earlier for germanium, silicon germanium. We start with a silicon wafer. we grow a germanium virtual substrate. The key here is to go through 2 steps growth, a low temperature germanium layer, high temperature germanium layer, and a thermal cyclic annealing to relax the strain. Typically, the dislocations in this layer is in the 10 to 7 if you have a very good material. And after that, we lower the temperature, we supply tin precursor, and we grow. So the best way to control the tin composition is just the substrate temperature. So we have what we do in the lab, be it for spin devices or for optoelectronic devices, is we grow a multiple layer, and we try to make sure that dislocations are confined between different layers and stay there. There is no propagation to the top layer. So here we grow a first germanium tin buffer, which is grown at a certain temperature. We lower the temperature again, we grow another layer, and lower the temperature again, and we grow another layer with the desired composition. And we keep the thickness here sufficiently under control in a way to avoid any dislocations. So we have, let's say, recipe to grow a different composition. Basically, the number of the bottom layers would give you an idea about the lattice parameter that you want to achieve for a given temperature. So for each decrease or increase in lattice parameter by 0.1 angstrom, we can increase the composition by 6%. And you can have either pseudomorphic or relaxed growth. Pseudomorphic incorporation, growth with pseudomorphic layers, the tin incorporation is about 1.3% for each decrease in temperature by 10 degrees, substrate temperature. So typically we grow germanium tin between 280 and 400 degrees. So if you start with a relaxed buffer, so it means a relaxed structure, you may incorporate much higher quantities of tin for each 10 degrees of decrease in temperature. So this is the same recipe that we are using for all kinds of devices. And here I show you how we can achieve this optically active whole spin quantum well. So we start, now we shifted to industrial buffers. We grow germanium tin, the first layer at one composition Y1. This is typically 4%. And after that, we lower the temperature and we grow a different composition, which is close to 8%. And once we achieve 8% that has a uniform and stable composition, we stop supplying tin and we grow a relatively thick germanium layer. So this germanium layer is highly tensile strained. And once we finished with germanium, we switched again to tin tetrachloride and we grow the quantum well. So basically what we obtain is a heterostructure like this. So this is your 8% buffer. This is the bottom barrier tensile germanium layer. And this is the germanium tin quantum well. And after that, we cap it with germanium layer. So the main challenge here is that the growth of germanium tin takes place at low temperature because we need to make sure that we have enough tin. But growing germanium with monogermane at low temperature is a very tedious process. So this would take hours to grow. So we are growing with growth rates that are comparable to the MBE. And this is coming from the fact that we are using this precursor, and this precursor does not decompose efficiently at low temperature. The problem is a high order hydride like digermane or trigermane are extremely difficult to find. So side note, if you have any supplier in India that can produce digermane and trigermane, I'm a potential customer, because that's a huge bottleneck that we have today, is that the growth will require extended times, and that influences this interfaces. So if you look at in high resolution images, so look at in the right here, this is atom probe tomography profiles. So this is the first buffer layer that shows 4.5%. The second buffer shows 8.5%. And the quantum well, remember from calculations that we wanted to achieve something around 15%, and this is what was our target. We were lucky enough that the first initial growth shows compositions above 17%. So in the fraction, we can see clearly that the quantum well a sandwich between tensile strained germanium layers. So as I mentioned, this is an image, but if I look at the much lower magnification, you see that the strain makes those quantum wells a little bit wavy at a large scale. So what they promised in the beginning is that this quantum wells should be direct bandgap. So we have to have evidence that this quantum wells can emit light, and we do. So this is exactly the same composition, 17%. What you see here, this is a room temperature emission. So we have clear photoluminescence emission from these heterostructures around 450 millielectron volt. And as we decrease the temperature, there is an increase in emission energy as you expect from the band structure. Something that we still cannot understand is that there is an emission line that emerges as we cool down. And we are still trying to figure out from where this comes. But we tested different structures. So we have reference structures that have only germanium-10 without the top barrier, so there's no confinement. And the emissions are completely different. So we see that these lines are room temperature emission from the quantum well itself. We run KP calculations. This is calculations showing the band gap versus the measured values from photoluminescence. And this is also confirmed that the thermal behavior is exactly how we expected from a direct bandgap germanium-10, 17.5% in composition quantum well. The interesting thing here is that we have a type 1 quantum well, and I don't have time to actually dig deeper on this, but this is by itself is really interesting. We were interested in really what happened to a whole spin here, but when we developed this heterostructure, we found that the electron spin is actually confined in gamma band, and which means that we have a heterostructure that can also be used for a gamma electron spin quantum dot. We are still figuring out how we can prove that we have electron transport as well. We did some whole bars on this, but the mobility measurements are not yet conclusive. It's a little bit tough because we have combined effect from holes and electrons in this. But next time I will have more data in that regard. But this is, think of it, germanium-10 heterostructures exactly like gallium arsenide without nuclear spin problems. So we can actually engineer a gamma electron and get rid of all the problems that in silicon quantum wells when you have to deal with this valley splitting and inter-valley scattering. The only challenge that we need to figure out is that unlike gallium arsenide, germanium-10, it's not an ordered alloy, which means that we have some scattering that might actually limit the mobility. We did some transport measurement in different quantum wells, and the mobilities that we measured are higher than 20,000 in highly compressively strained. So we have hopes that this quantum wells can show mobilities that are above 50,000 or 60,000, which is the territory when you can actually have good material to fabricate quantum dots. So let me just finish with I mentioned a lot about the G factor. We did some magnetophotoluminescence measurement just in different alloys in germanium-10. And if you are familiar with germanium, if you look at the data, the G factor is between 1 and 2. And if you take germanium-10 alloy at 10%, 8, which is a direct bandgap material, the G factor, the effective G factor is around 8 and around 9 for 8.7%, which is here the band structure is complicated because we have contribution from both gamma and L valley. So yes, we expected to have a higher G factor in these alloys, and the first measurement confirmed this. So I will just take you to as I said, I have a third section on light hole. I will skip it, and I will give you just the key point to remember. Group 4 materials There is all the technology argument that these heterostructures are compatible with silicon, but the fascinating aspect is you can play with these isotopes and you can push the growth part to control this subtle effect, but also you can push the metrology in and make sure that you have the capability to look at this subtle effect and measure them accurately. I showed you an example how one can solve all the challenges with the growth, which is practical challenges, not scientific challenges. You don't want to waste a precursor because it's difficult to obtain, and you want to make sure that you don't have any cross-contamination by using different precursors from the reactor. And we achieve heterostructures that are quantum dot quality. And in the third element, I showed you that we can achieve direct band gap germanium-tin quantum well. And I showed you an example at 17.5% with emission around 2.5 micron at room temperature. I didn't have time to show you the light hole, but I will be happy to answer to your question. So thank you again for your attention. I'm happy to engage with you in the questions.
Thank you, Oussama. So the floor is open for questions.
So this is Shuddha here. So thanks for the nice talk, Oussama, and it was really a lot of new development for the whole systems, as I can see. I have a bunch of questions. I mean, maybe I start not in any particular order, but you said that you are getting these buffers actually commercially from some source.
Yep.
Question is, do you see any need or advantage in doing CMP before the growth, or that's not really something that concerns you?
Here's the trick. I can show. We had a conference on silicon epitaxy. So to answer your question, I don't think we need CMP, to be honest with you, but based only on whole mobility measurement. So my friend in COLIT, Jean-Michel Hartmann, he's working with same silicon germanium heterostructures, the same composition, the same stack, the same thicknesses. And he showed me his result in mobility measurement after CMP in the buffers. So he has an industrial reactor. So he grows and he takes the wafer, CMP it, and put it back. To make a CMP compatible growth, you have to add a few microns buffer, so you don't need to remove to make sure that you will have sufficient thickness to remove and reduce the roughness. So in our devices, the first batch of devices, we didn't do any CMP. So we took the wafers as grown and we grow on the top of them. And we have slightly higher mobility in our devices than the devices of Jean-Michel Hartmann. So CMP is not critical, in my opinion, in germanium-rich silicon germanium heterostructures. But in germanium-tin, I think it will be extremely important to develop CMP. And CMP in this heterostructure would be extremely challenging. It's not that easy. Because one need to grow. Either you develop a very gentle CMP that can remove only a few tens or 100 nanometer, make sure that you get a better surface. But having a standard CMP from industry for germanium tin is not going to work because the thickness of those layers is very low. So yeah, so answering your question, for silicon germanium we didn't see any difference, but for germanium tin we anticipate that CMP will be critical.
Right. So I go to my next question, which is more of a surprise. Did you say that silicon 29 could be seen up to 2 micron? Or did I hear that wrong? Or 1 micron, I think.
No, it's silicon 29. If
from the APT data.
Yeah. So here, this is I'm showing you the spectra of germanium 70. Germanium isotopes.
Right.
So, yeah, so here, 2 micron, we start growing without natural germane for 2 microns. So you see that germanium 70, germanium 17. So we grow 2 microns, but since we grow silicon germanium with natural precursors before this 2 micron, the reservoir effect from this growth in the reactor, even though that we grow 2 micron, was not eliminated. We can still see, you can see it here that there is a slight bump here, and that's a significant amount of germanium-73, except that it's buried in the thermal tail of the stronger germanium-70P. But yes, even after 2 micron of growth, the reservoir effect is not suppressed.
So the reservoir effect is necessarily saying that in the ambient there is still natural germanium.
In the reactor. In the reactor, it might be somewhere in the shower head, somewhere in the sidewalls. So we couldn't eliminate it, and the point here is that it doesn't make sense to grow 2 microns of isopropyl purified layers to end up using only the top 60 nanometers.
Right. Yeah. Which essentially says that you just want to eliminate any natural germanium from your reactor altogether, and that's the whole idea.
That is, we don't grow natural germanium anymore, so we do that ex situ.
Yeah. Okay, so the third question is more related to what's happening with this quantum wells. I mean both germanium tin and germanium, in the sense that do you have any transport data from where we could see how the quantum Hall data looks, for example, or the mobility? I mean, mobility is fine, it's just a number, but there is more to it in terms of the Hall data.
Yes. Sorry, I don't. You can. There's an in-depth discussion of the transport measurement in this paper.
Okay.
I didn't show it. I would just for sake of time. So we have transport in this germanium quantum wells. There are some interesting features in their behavior. For germanium tin, the direct band gap quantum wells, I think as I speak now, the students who are measuring the transport of these quantum wells, they managed to achieve the first stable Hall bars. We don't have data for quantum wells that are direct band gap. The challenge, again, if I show you the heterostructure that we are working with. So imagine you want to make, let me take you here. You want to make a Hall bar in a heterostructure that is absolutely not yet investigated. So think about which dielectric. Dielectric is easy, which side of the contact, how you can diffuse the contact. The thermal budget here is completely different than standard quantum wells like germanium, silicon germanium. So we're learning our way in just how to make the contact work. The good news is that we have devices that are working. We did actually put a paper published last year with a team in Japan and Germany. We worked with germanium tin quantum wells that are compressively strained.
Right.
And we look at the behavior, the strength of spin orbit coupling, how it changed with strain. We also measured the mobility, and the mobility in those devices something like 18,000. I don't have the reference, but if you reach out, I can give you the paper.
Certainly.
So if I put just the materials hat, I think one of the major challenges with this material system is we have to establish everything from scratch. So there is nothing we can build on in terms of how you make the contact, make sure that what you are measuring is not something else other than the transport in the quantum well. So you have to deal with the background doping because these materials grown at relatively low temperature. You may have some vacancy trapping, charge and dislocations that can actually contribute to background doping. We might have to handle also the particle conduction if there is any in these devices. So yeah, there are so many open questions, and whenever we have any transport measurement, we second guess ourselves because this is exactly the inherent behavior of the device, or there is something else. Sorry, I don't have any data to show you now, but I can share with you the paper, at least showing the transport. There is a group in Taiwan a couple of years ago. They published a paper also on compressively strained germanium tin, not direct band gap. And one of their conclusions is that the high strain, killed the advantage of that you might have from a strong Rashba expected from tin, a large tin, germanium tin atom with large, the fraction of tin that is a large atom. But again, this result is yet to be reproduced. Reach out to me. I can share with you this data, so what we publish in terms of transport, and also what other people publish. But again, there are so many open questions about the stability of the devices and what is coming from the quantum well, what could be coming from something else.
Thanks. So just one last related question, which is a small one. So I'm assuming that you don't need to gate these structures to get carriers, or are they already populated, or do you need to actually induce?
You have to gate them. So yes, you need to gate them. And for optical, the next step for us here to achieve the optical activity or to design something that can be used for momentum transfer, we need actually to add p-type doping and germanium and barrier.
Yeah, which is probably not the best for the mobility once again. I mean, so.
I'm not concerned, to be honest with you. I'm not concerned about mobility because your quantum dot, it's a super carrier device. Yeah. So I know that there is an emotional attachment to high mobility, but for us, I don't think it's that critical as long as your material is high quality. So the mobility is used as a first order parameter to say if the material is good or bad. But you can have very good material, and you can do it in purpose to actually, by including dopant, that you can hamper the mobility. But again, that would not affect the quantum dot behavior.
Sure. Thank you. Thanks a lot.
There's one more question.
Thank you for a fantastic talk. I have a very brief question. When you talk about this isotopically pure either silicon, germanium, etc., is the only way to get the isotopic purity still centrifugation, or are there other methods to do that now?
There are methods. I think there is. I have to be careful because there are some confidential information.
I see.
So,
okay.
So there is, all the materials that was available some time ago, and it's still circulating now. It's the materials that were produced by the Russians, and the Russians, they are using centrifuges for purification. But there are now companies in the U.S. Within the framework of the CHIPS Act to, let's say, to stimulate semiconductor manufacturing in the U.S. and to have autonomy in terms of manufacturing. So these companies are trying to build entire supply chain for semiconductor isotopes. So there is a company called General Matter. They have been awarded just recently $900 million to establish enrichment facility for uranium, and they are moving to silicon germanium precursors. They are not using centrifuges, so they are using different processes. There are other facilities in the US that they are using thermal diffusion. But General Matter are keeping their process confidential. So they have a huge installation in Kentucky, if I remember well. So there is, if everything works fine, I think within 5 years or 4 years from now, there will be more precursors available from U.S. suppliers, because the Russian option is not valid anymore. There is also a company in China that claims that they can purify silane with up to 5 nines in terms of purity. They told me that the first batch of their precursor will be available by the end of June. Again, they didn't share how they are making their material. But I would presume China, Russia, I think there will be a lot of centrifuges used because they don't care about energy. They have a lot of energy for that. In the US, I don't think that they are using centrifuges. They are using completely different processes. Yes. Sorry, it's a long answer.
Thank you. Thank you.
There is a lot of moving target in terms of precursor development, but there's a lot of pressure from different labs to get access to especially germanium isotopes. So Intel is looking for this. If I go back, one of, let's say, very well studied heterostructure. So this one, if you look at all the papers published in the last 20 years, they are using only silicon-28, but in the barrier, they still have germanium-73, and that's a limiting factor. So this is why these labs are looking for germanium isotopes to solve the problem. Forget about the hole, which is coming with a bunch of problems. Just electron spin, which is a well-engineered heterostructure. There's a lot of papers on this. A huge community. They are still struggling with getting rid of germanium because your electron wave function will reside at the interface. So we have a fraction of the wave function that will feel the silicon germanium alloy, and in that alloy there is germanium-73, and that's a major factor. So there is this pressure in getting access to germanium isotope from American companies and labs.
I guess Lawrence Semiconductor has started putting purified germanium in the barrier, right?
I cannot answer the question. I have an NDA with them. But I think there is. I know IMEC. IMEC, they have access, and even QTech and COLT, they have access to germanium-73 depleted precursor. But I heard from IMEC that precursor is highly contaminated with oxygen and carbon, and it was produced by Air Liquide. And the problem with Air Liquide is that the quantity that they produce was not sufficient, so they can purify it chemically. So now IMEC is looking for all people who are interested, so they can put a huge order to Air Liquide, so Air Liquide can take that seriously and chemically purify it. And I presume that Lawrence also has access to that germanium. It's not purified; it's just germanium-73 depleted. So you remove germanium. So there is a mixture of germanium-70 and 72, which doesn't matter because you did just get rid of precursor. I know HRL in California, they have access to that precursor, or at least what they told me. But again, I cannot find any paper on this. So, and this has been around for 3 years now. So 3 years is enough actually to show that you can grow this without issues.
Okay. Any last questions, comments? If not, we thank the speaker once again. Oussama, thank you for the nice talk.
Thank you. It's my pleasure. Take care, and hope to see you in person one day.
Yeah. Same here.
Bye. Take care.